Several months ago, we had as our guest at a colloquium Dr. Dixie Lee Ray, who talked about a number of environmental concerns. Paraphrasing some of Dr. Ray's conclusions, environmental phenomena are very complicated. Natural processes can affect the environment to some extent much more than human processes can. And one should take a great deal of caution before one changes the scale and scope of human activity because in many cases the cure can be somewhat worse than the disease. We have an environmental ethic working group at the laboratory called Our Common Ground that was very interested in Dr. Ray's talk and asked that we present an additional colloquium which would look at one of the aspects, one of the concerns that Dr. Ray mentioned, and consider it in some greater detail. And thus this colloquium was born, and it gives me great pleasure to be the host of the colloquium and to introduce our speaker, who is Chick Keller. I've known Chick since I've been at the laboratory and have great respect for Chick as a scientist and an administrator, and I'm pleased to say he and I have been good friends. I would mention that Chick has an enormous range of interests. The range of his interest is in part indicated by his educational experience, which involves 2 bachelor's degrees, one in philosophy and one in physics and mathematics. And his PhD from Indiana University was in astronomy and astrophysics. Chick's interests are actually much broader than this. Many of you will remember that he writes an occasional column on wildflowers for the Los Alamos Monitor. He's also published a small book on wildflower identification. Chick has been interested in atmospheric phenomenon since 1977 as an outgrowth of his group's work on nuclear fireball atmospheric effects. He was responsible, with others, for forming the DOE's ASCOT program, Atmospheric Studies in Complex Terrain, which led to modeling in Northern California and in Colorado. Bob Malone joined Chick's group in 1981, and the two of them pursued an interest in the so-called nuclear winter phenomenon. Chick is now director of the Institute for Geophysics and Planetary Physics, and for those of you in the back, there are still some seats in the front, which we invite you to take. As director of IGPP, one of Chick's main focus areas has been, in fact, on global climate change. Chick, as director of the University of California's Institute for Geophysics and Planetary Physics, has set up a number of interesting collaborations with the University of California. One of these with Scripps Institution of Oceanography in the area of global change. I've always looked with a great deal of envy on Chick's job as director of the IGPP. More than once I've told the director, Sig Hecker, that if he ever wants to get rid of me as an associate director, please give me appropriate notice so I can get rid of Chick as director of IGPP and try to sneak into that job, because I think it is indeed a fun one, and I'd have to admit Chick is filling that job, I think, to perfection at the present time. It gives me pleasure to introduce Chick Keller, who will speak this morning on the topic, Is Our Climate Changing? The Situation, the Threat, and the Challenge. Chick?
Thank you, John. Thank you, John, and good morning. I was a little worried you would be greeted with a sign that said, global warming talk canceled due to snow. And that will be part of my discussion about why you can have more snow when there's global warming. We global warming people are very slippery, and we can make anything look like global warming. Before I start my talk, I'd like to point out, especially to our visitors, that in the event of an emergency, these 2 doors both open immediately to the outside, so you can breathe New Mexico air the minute you're out there, or back out through the doors and to the right for those of you in the back. The view graph I wanted to put up so that you could just get a feeling for looking at our Earth. It is an absolutely unique object in the solar system. There's anything like it. And it has to do with the fact that it can cool itself and warm itself with its atmosphere and its oceans. And that's what I'd like to talk about today. And I'm going to go rather quickly because I'm really hoping to not be too late, but when I got the talk all together, it was a really good 3-hour talk, and all the things that you just had to know. And so I'm going to go very quickly, but I'd like to leave some time for questions. First of all, I would like to thank Common Ground for requesting this colloquium. The topic of global change, and particularly global warming, has become quite controversial. After general agreement with the original calls to alarm that culminated in Jim Hansen's 1988 testimony before a heat wave and drought-stricken United States Congress, there has arisen a vocal and determined backlash questioning every aspect of the global change scenario. Most of the people I talk with have concerns about just how real and significant the warnings are. In fact, the thinking on global change has polarized around the question, are humans causing global change or not? This is unfortunate because it diverts attention from the true significance of the issue, which is how to learn fast enough about global climate dynamics in order to evaluate both human and natural threats to our perception of the well-being of this good Earth. This morning I hope to impart to you not so much the answer to the polarized question as the excitement and the importance of the study of how the Earth's atmosphere and oceans operate in making this planet habitable for a seemingly limitless variety of life. The story will address our immediate concerns about global warming, but will, I hope, give you the broader message that climate dynamics must be understood as well as possible, as soon as possible, to ensure humankind's stewardship of the Earth and its creatures. Let's go to the first view graph. There you are. The first one says global warming is real. The second one says there's no scientific consensus. The third one says the greenhouse report puts down the dissenters, and then the Academy split over the greenhouse. And so you can see everyone has a headline to suit their own taste. And finally, down here, some experts say we can adapt to what's ahead. I liked what me worry, global warming won't be so bad. Let's go to the next view graph. Here's science goes to the newspapers. We learn that clouds, you have to know all about clouds, and so their storm link is, storms are linked to the whole situation. And you keep going down through lots of these things. I like this one, global warming for fun and profit. That's Amory Lovins, if you know Amory, and he is quite articulate about that. But finally, you get to ozone depletion in the Arctic, and then this last one, which was just came out about a month ago, that the summer ozone loss is now detected, and that's a cause for considerable concern. Let's go ahead. That's supposed to be a huge ice sheet coming down the middle of Fifth Avenue, and it says they did it again. Not a word in the weather report about the coming of the Ice Age. Go ahead. I'd like to talk a little bit about what it is that we really are facing here. And to do that, I have to give you a little primer of some things. So can you hear me? Is this is working? You can all hear? This is the Earth's atmosphere, and then this deep blue is the ocean. And the first thing that happens is that you have the sunlight shining down roughly at the equator, and it causes great uplifting of air, these two great Hadley cells which turn the air north and south. What the atmospheric engine is doing is having the sunshine shine down here mostly, heat the atmosphere up, and then it tries to carry the heat up to the north and south poles away from the equator. And it does that. But when it tries to do that, it runs into the fact that the Earth is spinning. And when you try to move on a spinning Earth, you move from where your rotation speed is about 1,000 miles an hour to up toward the North Pole, where, of course, you're doing nothing but 24 hours going around in one circle. And that causes the descending air to spin around in great cyclones, and we get our wonderful mid-latitude weather patterns. And then finally, there's another one of these patterns, circumpolar patterns, which allows you to have very interesting weather effects at the poles, including the famous vortex, which gives the ozone hole. Now, also in doing that, you see that near the equator, the winds blow primarily from the east to west, the famous trade winds, which brought the ships trading around the world. And then the westerlies, which allowed Columbus to get back, occur at just slightly higher latitudes. We're in the westerlies, and then there's another set of easterlies higher up. So this is a very complicated weather pattern of things moving up and down, north and south, and east and west. The oceans are doing similar things underneath, and it's this entire interaction which is the complex that we have to deal with. Go ahead to the next view graph. Now, this is my magic markers late at night one time. What we're doing with the Earth is the following. If this is the amount of energy coming in some set of units, and this is wavelength from ultraviolet and blue and green and yellow and red to infrared, the sun, which is a very hot object, 6,000 degrees, shines in through the Earth, and most of its energy is in a band like this. The Earth heats up to about 255 degrees Kelvin, which is very cold, and re-radiates the energy back out in an equilibrium. So then the energy in equals the energy out. And you can see these two little hills here are about the same. But the Earth re-radiates way out in the infrared. You can't see that. You can just sense it as heat. And at 255 degrees, that's not much heat, but it does it. Now, that brings up an interesting problem. If you look, the gases in the Earth's atmosphere sometimes are very transparent to the radiation. That's why when you look up at the daytime, you can see the sun, because it shines in. If this is absorption from no absorption at all to complete absorption, you see the ultraviolet doesn't get through here at all due to oxygen and ozone. And then in the visible, we call this the visible because it's the part our eyes are used to, there's a big hole, no big absorption, and so lots and lots of sunlight comes through here. And then out into the infrared, there's tremendous absorption, mostly by water vapor. You can see H2O here all over the place. But right at the middle of this big thing, there's a little bit of a hole. That's where the radiation gets back out. The water vapor is blocking everything else. And look, there's our friends methane, the chlorofluorocarbons, carbon dioxide, nitrous oxide. You see all these little things, and that's why they're called greenhouse gases, because if they fill up this little hole here, the radiation can't get back out. What will happen then? Well, the Earth will heat up until, and this will move this direction, and find other ways to get the energy out. And what has happened on the Earth now is, let's go to the next view graph. I kept that, it was supposed to be blue and red, but it's sort of green-red, but that's all right. And it's just sort of color coding so that you'll know this is sunlight coming in every time you see the green on the other view graphs, and this is the Earth trying to get the energy back out. The sunshine comes in, scatters off the dust particles in the sky and goes back out. That's why the sky is blue. It reflects off clouds and goes back up. It hits the ground and goes back out. After all, if you're out in a spaceship and you look at the Earth, you can see the ground. Well, you see it because the visible light is coming back out again. And so a lot of the sunlight just goes right back out into space. But an awful lot of it does heat the ground, so the ground re-radiates and tries to shine back out into space. And what it does a lot is to run into other molecules and gas in the atmosphere and shine back down to the ground. And for that reason, we're lucky. See, if there was no atmosphere in the Earth, the temperature of the Earth would be that 255 degrees, and 273 degrees on that scale is freezing. And so it's below freezing. But with the atmosphere we have, because of this interaction in here, the ground actually has heated up a whole lot, 30-some degrees centigrade. And so we have a very nice habitable Earth due to mostly water vapor and some carbon dioxide, which keeps us warm. The rest of the atmosphere heats up, and at some height in the sky, if you go far enough up, there's a surface that would re-radiate at that 255 degrees, and that's how we keep the Earth from heating up too much. It gets on out. Let's go to the next graph. These are clouds, and I just want to go through clouds quickly because clouds are the whole game in the uncertainty. Most of the uncertainty in predicting the weather is in clouds, the climate. First, if you're down near the equator, you get these huge cumulus clouds. We get them here, but they're even much bigger at the equator. The tremendous amount of heat that the sun puts in the equatorial regions, most of it is carried aloft in very large clouds. The trouble with the clouds is that the Earth can't radiate out underneath them. So this red thing goes up and comes back down. A little bit of radiation goes off the tops of them, but they're so cold that they don't really radiate very much. And the only thing they do is they reflect sunlight quite nicely. And the problem we're worried about in global warming is if these clouds get even higher because there's more energy, this radiation off the top, they'll be even colder and there'll be even less radiation off the top. These big clouds do something else. The winds shear along and blow the moisture away, and it quickly freezes into the next set of clouds. Let's look at the next view graph. And these clouds are ice crystal clouds called cirrus. They're very high, more than 4 miles high. And what you're seeing here is you don't see any shadows. See over here, we're going to talk about some clouds that have shadows. These don't have any shadows to speak of. These are the ones that the jet trails you see in the sky. And the problem with them is they let the sunlight in, but they don't really let out much infrared. They really block the infrared. So if global warming makes higher, big cumulus clouds, which don't radiate much off the top and which make much more ice crystals, we'll have what's called a positive feedback. The warming will make things which trap more energy, mostly in the water vapor, not the CO2, which will then heat us up, and it will get a positive feedback, which will go on until we get some negative feedback that stops it. The good clouds to stop global warming are these little fellows, which are only a mile or two high. They're down where the Earth is warm, so they radiate very nicely. I didn't put that on. They reflect a lot of sunlight, see those shadows, and so they're good clouds. So the little wimpy, rainy clouds that you see, marine clouds, the big decks that go across the United States that aren't very high, if global warming creates those preferentially, then that will be a negative feedback, and we won't get much warming. What is the answer to this whole thing? We don't know, and I just wanted to go through that quickly with you because that's where most of the uncertainty is. So they sort of cloud the issue, if you will. Could we go to the next view graph real quickly? The other game is the oceans. The oceans have tremendous heat capacity, but the oceans are really sort of two things. They're a very thin mixed layer at the surface, and the layer is mixed primarily because the sunlight penetrates down, warms up the water, and it tries to get buoyant, but also because of the winds just sort of stir up the surface, and you get a lot of mixing that way. But you see that's not very effective. It's not as if the ocean is mixed down a mile deep or something. Some places the ocean layer is mixed only 100 meters thick. And so while people think that there's this huge ocean that can take up all this global warming, there's only this little thin layer that can do it. And there are some indication that the layer is very carefully trying to take up that heat, but there's more heat than it can take up, we think. However, there is this other circulation that's been discovered. Over in the Indian Ocean here, and some of this part of the ocean, they're very, very warm, shallow water, and that has formed into a little river-like current, like the Gulf Stream. And it comes around Africa, it goes over, it actually doesn't go this way, it goes over and slams into South America, then comes up and goes up in the Gulf Stream. And when it gets up in here, it has evaporated a lot of its moisture, and it's very salty. And so when it gets up to where it's cold in the North Atlantic, having heated up Europe, it sinks. And in a very deep return convection, very deep, cold, salty water comes all the way back down here. So you have this little conveyor belt. It takes about 10 to 100 years for it to make one trip. Now that's a way to take that warm water and dump it, deep six it, if you will, into the ocean. And that effect may indeed be going on, and it may be causing a lag. One of the reasons we're not heating up as much as we thought may be due to the fact that there's a lag in these kinds of things. I'd like to go on as quickly as I can. You have to really put those two things together in order to estimate what's going on. That's the end of our tutorial in global warming. But the next thing I want to talk about is Ipcc. That's becoming a famous and to some people infamous acronym for the International Panel on Climate Change. The United Nations, the World Meteorological Organization, and other organizations called together 170 scientists, 25 countries, workshops, lots of authors, lots of reports. And when the report went out, there were 200 invited reviewers to comment on it. It was an attempt of the scientific community to get away from alarmism, to get away from minimalism, and to try to look at the whole issue and say what could be said about the global warming part of global change. In August a year ago, the Ipcc report came out. The The reason I'm bringing this up is you're reading in the newspaper, lots of people and in magazines, what other people say this report says, and I think it's only fair that you get a chance to read what it says yourself. There are 40 copies of it on the table in the back outside that you're welcome to have if you want one, and then if they run out, there's a sign-up sheet. We could get you some more. This is quite a nice summary, and then you can get on our books and buy the whole 300-page report if you'd like to do that, and some people might indeed want to do that. It has 5 sections. The most important ones are the science, the impacts, and the response. And those headlines about the National Academy of Sciences saying the impacts, and there's quite a bit of discussion here at this point about what we should do, and you can imagine the discussion at response. Let's go ahead. I'll be talking about Ipcc things most of the time. Here's a consensus of what they said, and I'll go through it really quickly. The warming will likely be large enough to have significant social effects. All right. Sea level will probably rise. It can rise if just the oceans just get hot. You don't have to have anything melt. The oceans, warmer water expands, and you can get a rise just due to that. One of the big concerns is that North America and Russia are where most of the wheat is grown and what have you, the bread baskets of the countries. And the models are predicting that those interior land masses might dry out ever so slightly. They don't have to dry out very much. CO2 will double by the year 2035. We'll talk more about that if we don't make any effort to slow things up. This is a very significant one. The warming is real. That's a significant statement. They came out and said, and keep in mind that centigrade or Celsius, it's not Fahrenheit. We'll talk about that. 1 degree Celsius is roughly 2 degrees Fahrenheit. So when you hear of a 1 degree temperature rise, it's really 2, and if you hear of 5, it's really 10, in terms of what we think when we hear the weather in the evening. Detection of greenhouse warming with high confidence will require a decade more of waiting. And I don't have time to go into this too much, but I'm convinced that if you only have data, you don't do any computer modeling or theoretical interpretation or anything like that, we will never convince anybody there's global warming, because you can always say there's something else. We're going to have to make models, we're going to have to test them, we're going to have to, decide what the crucial things are about whether this real warming is due to humans or just due to climate variability. Let's go on. Oh yes, I like this graph. This is Celsius. Let's go over to Celsius place. It's only 36 over there. You see, you have to keep in mind that when they say 2 degree warming, they're really saying 4 degree warming in terms of the weather. Go ahead. Now for the evidence. I think this is an important thing to understand. My background is astrophysics, in which the game is to be smart enough to figure out the answer before you have many facts. And so astrophysicists are a uniformly nasty bunch of people. They fight with each other all the time because they never have enough facts and they always have strong opinions. And this is just a situation which is what a scientist really should do. We should try to get the answer on the least evidence, get ahead of the game, if you will, but it causes this problem. Let's go ahead. All right, what are the greenhouse gases? Keep in mind that the main greenhouse gas is water vapor. But this is a little pie chart to give you a feeling for the human-generated greenhouse gases, which are only a small percentage of the whole thing. But only half of it's carbon dioxide. The other half is roughly split between chlorofluorocarbons and nitrous oxide and methane. And the reason is that these have radiation properties and are interacting with the atmosphere in a way which makes them more effective than the CO2. So a doubling of the chlorofluorocarbons is very effective in blocking radiation. A doubling of carbon dioxide is effective, but not quite as much. Let's go ahead. Don't try to read any of the numbers or things. I just wanted to give you this feeling for the shape of the curves. These two curves start around 1800 and go to around 2000, and they show what the CO2 used to be, and then they show it rising. And now they show why we're really concerned. It's rocketing up very rapidly since about 1960. On this scale, if this is 1900 to 2000, this would be 2000 to 2100. Sometime in this time frame, the prediction is that this thing will go up, higher than I can point this graph, which is what is doubling. This is only an increase of about 1/3, so 3 times more to get there. And you can see, first of all, why we probably haven't seen very much warming and why we're liable to really have a big problem if this goes up. Here's methane doing the same thing. A hopeful thing is chlorofluorocarbons. Now the scale is 1960 here, 70, 80, 90 to 2000. And you can see when Sherry Rowland published his famous paper saying that chlorofluorocarbons in stratosphere could take out ozone, people got responsible and began to do things. And so we have reduced our chlorofluorocarbons, and we're reducing them farther. The difficulty and the problem that we're talking about is this is what I call a Rachel Carson silent spring thing. Rachel Carson said all the animals and birds and everything are all going to die if you don't stop using DDT, so we stopped using DDT and everything was fine. The chlorofluorocarbons, we can do that. But supposing we say, okay, let's stop using, producing CO2, that's a much different problem. And so that's what all the shouting's about.
Is that a suppressed zero?
Suppressed zero. Chlorofluorocarbon is at zero. No, this is not zero. This is the level of CO2 that's been in the atmosphere for the last few thousand years. Sorry. Go ahead. Well, here it is. If you haven't seen it, you haven't been around. This is the famous set of sea surface and earth surface temperatures. The global average shows that around 1860 to 1900, things were bouncing up and down. These are the big excursions, and then this little line here is sort of the 5-year average. And then sometime around the beginning of World War II, or maybe just a little later, the temperature began to rise very rapidly. And around the beginning of this is World War I, World War II, the temperature rolls off and level and then takes off again. What a very strange stair-step thing. Doesn't look at all like the greenhouse gas curves I showed you. The southern hemisphere looks like it's not doing very much and then gently goes up. The northern hemisphere has an actual decrease in temperature here, which led people to predict there might be another ice age coming in this time frame. And that's not so laughable. I'll come back to it because there is a possibility that we are in a period of cooling, and that the greenhouse gases that we're putting in the atmosphere are actually modifying that. But this certainly these are temperature records which show a general increase in temperature of about 0.5 degrees Celsius, but which don't look anything like any of the computer models. The computer models predict about twice as much, and they do have quite a bit of variability in them, but they don't have anything like a decrease like this, which is somehow characteristic of the industrialized land masses in the northern hemisphere. The ocean, not industrialized, southern hemisphere doesn't seem to have it, except in reflecting that.
How is that measured?
The temperatures are measured all over the world by lots of little thermometers and gauges outside of airports and what have you. People worried about a heat island effect, and that's been taken out of these graphs as well as people can do it. And I'll say some more about temperature. Let's go to the next graph. This very noisy graph from about 1978 to about 1988. Probably many of you read the thing in the papers about a year ago. NASA satellite information for 10 years shows no warming, unlike the ground base, which showed warming. NASA had a satellite which was looking down. It's a microwave sensing unit, and it looks down, and it doesn't really see the surface, but it sees down into the lower part of the atmosphere. And it was getting a record which looked like no rise in temperature at all. Well, the point is we're looking for a very small change in temperature, 1/10 of a degree Celsius. And so we've really expanded the scale now. There's not even 1 whole degree Celsius in this whole graph. So it's looking very noisy. But this is the latest reanalysis of the whole thing in which everybody got together. This is surface measurements here. And finally, these are radiosondes which are sitting on the ground looking up, and they sense the part of the atmosphere that the satellite sensed a little better than and more representative than the surface. And look at that. You've got almost complete agreement among these 3 curves. And what the satellite did was, far from trashing the surface information, you're able to use the satellite information because you have it. It's completely representative everywhere. You're able to use it to study how representative the surface information was 100 years ago or 50 years ago. And you're able to use the few radiosondes, maybe 100 or so around the world, to show that they're represented enough to actually give you a global temperature. And so the satellite, working with the surface measurements, have really strengthened that curve I showed you before. We really are getting very confident of our temperature measurements. And it's just too bad that the initial press on the satellite information was that they were going the other direction. Next graph. This was supposed to be red and blue, and it was when the fellow at the conference two weeks ago showed it to me, showed it to everyone. But when he sent me a copy, he sent me a Xerox copy of it, And so this gray area is, you take that to be blue, and this black area is, you take that to be red. What is this? This is the surface temperature anomalies, because after all, people don't live in an average temperature. They live someplace where there's the temperature representative of that. You hear that the United States isn't heating up at all. What's all the fuss about? And the reason is that the west side is heating up and the east side isn't. That's what, you see. If you get the same thing, you could have the 20-degree rise in the northern hemisphere and a 20 degrees cooling in the southern hemisphere, and the average Earth temperature wouldn't rise either. The reason I'm showing you this is to show you that it is very spotty. The climate is a very complicated thing. The weather patterns are very complicated. But the fact of the matter is that something very strange is happening. There's a lot of high-latitude warming, and the models predict that. The models don't predict as much warming in the mid-latitudes, and so this information here seems to say that the models are wrong. Well, this is where El Nino occurs, over here in the Pacific, and we've had larger than normal El Ninos in the 80 to 89, so you could say, well, this is anomalous, the models wouldn't predict that. The big question is why the models don't predict this enormous warming in the Indian Ocean, which is terribly important to the Earth's climate. And that's one of the big questions. But it was gratifying to see that the warming in the higher latitudes that's predicted by the models is seen in this little 10-year run. It's also seen in glacial runs, in paleo runs, the last 100,000 years or so. Let's see the next view graph. Another thing is an interesting one. People are saying, well, you know, it can't be warming. We've had all these killing freezes. The fruit belt in Florida is getting wiped out every year, and so there can't be global warming. And this is a graph which I think speaks to that issue. This is the average temperature of Florida for 100 years. You can see it going up and down with very large excursions. You know, you want to look at temperatures. These are degrees Fahrenheit now, so you have to divide by 2 if you want to get back to Celsius. The thing that's interesting is these little dots are the times of severe killing freezes of the fruit crop. And the thing that's really amazing is, of the 14 that are here, 6 of them are in the last 10 or 11 years. And what that may be saying is something that some climate scientists are beginning to work on really hard. As you try to drive the Earth's atmosphere with global warming away from an equilibrium with the Earth's oceans, which will lag behind it, you may end up with a situation in which there is a very small average change, but there's a tremendous variation. You only need you see an orange or a grapefruit in Florida doesn't care what the average temperature is. It just doesn't want it to go below 28 degrees one night out of the year. That's all it wants. And what we can have is we can have a higher frequency of extremes. You see, these things are saying, oh, the average temperature is warm enough, but on one night out of the year, the temperature went way down to here. You see, and it was doing that. So you can expect coldest, wettest, driest, warmest, in a situation where you're driving the climate away from an equilibrium situation, a higher frequency of extreme things. When they fold them into the average, you'll lose those, but that doesn't help when you have a wheat crop if you get one freeze in the middle of August. Let's go to the next view graph. Can we go on? This is the last 160,000 years taken from an ice core in Antarctica that the Russians have drilled. And so you can watch the temperature rise. There's a big glacier here. Temperature rose to an interglacial, up a little hotter than that 0 is sort of our normal Earth temperature that we like now. Drop back down, rise back up, and you see this little decay? We're heading away from the interglacial. We're cooling off. And so it may be that one of the possible answers for why we're not heating as much as the models say is that we're superposing a human-generated warming on top of a natural variability which is trying to cool us off. These aren't things that we know for sure. They're just things that we're asking for questions. Here's carbon dioxide and methane, which seem to vary along with this kind of cycle. Whether they're leading it and causing the change or lagging it, just following the change, is being worked on now. Let's go on quickly. The threat. I like John Muir and several other people at the turn of the century, when they were decrying the tremendous devastation that they saw at the turn of the century. My, what would they say now? They said this: at least they can't mess up the atmosphere. Now we can't write that either anymore. Let's go ahead. The threat, speak to that view graph in a second, but the threat comes from the fact, if I have a globe of the Earth that's about 20 inches in diameter, the atmosphere as high as Mount Everest, namely the atmosphere that has the convection, most of it, and what we breathe, and most of the density, is how thick? It's about as thick as a thick view graph. It's about as thick as a thick piece of plastic. That's all it is. There isn't much atmosphere, and so it is possible to do some damage to it. Another figure of merit, if you will, is if you take all the people in the world, 5.5 billion people, how many acres are there in the world for people to live on? If you exclude mountaintops and hard deserts and this and that, every man, woman, and child has less than 2 acres in which to grow their food, get their clothing, build their automobiles, listen to their CDs, travel to Europe in a 747. Each of you only has fewer than 2 acres. And in the best guesses of what the Earth's population is heading for, each person is going to have less than an acre. Now, to show you that a little differently, due to the Green Revolution and the increased use of new irrigation, which is by and large a non-renewable resource, we're drawing down a lot of our aquifers with irrigation. We've caused this enormous population explosion, but we have succeeded in feeding it. However, in the great drought years of 87 and 88, the Earth produced less than an 8, began to eat into its reserves so that it was down to not much reserves. In fact, in 88, the United States, for the first time in its history, ate more than it produced. In 89, we thought, okay, it's a good year, no drought, things will be better, and we still missed some 1%, or 1/10%, I guess, we're still in a deficit. It is this context, when we talk about threats, we have so fine-tuned the food production of the Earth to feed this incredible population that global warming doesn't have to do very much to us to wreak havoc. And it is in the context of that threat that I think we need to discuss this. Let's go ahead. I just decided to summarize just a few. I'm not good at threats, so this will be the weak part of the argument, of the talk today. But there could be losers and there could be winners. We've talked about some of this. Bill McKibben, in his book, The End of Nature, which I recommend everyone to read, doesn't talk about what we can do to save the Earth or bring it back or make it natural. He just waves a fond farewell. We're losing the natural world as we know it. We're turning the Earth into a spaceship, and we certainly can adapt, and we can make it there. But the increased temperature will probably pose great danger to the flora and fauna, which can't adapt like we can. And they will also change considerably the way the society lives and what it does. Decreased soil moisture is one of the big things. It doesn't matter if we have increased rain if the evaporation due to the increased temperature causes decreased soil moisture, because this is where our plants, we don't have many air plants that we turn into cash crops. Larger, more frequent extremes, we've talked about that. Sea level rise, the country of the Maldives would cease to exist, and there'd be great difficulty. And it's not just like the rising in level of a lake. This is the difference between very large storm surges and high tides and things, which can cause even more trouble. And finally, the ozone depletion of the stratosphere, which lets the ultraviolet rays get in, and who knows what they do to the phytoplankton, let alone to the human population. Winners? Well, gee, it'd sure be nice to warm things up in cold regions. The changes in the rainfall, some places there'll be more rainfall and there'll be better crops and what have you. There will be winners. The increased CO2, we know, makes the plants grow better. And possible, if we are coming out of an interglacial and headed toward a cooling, we may actually find that we want to put more CO2 in the atmosphere, because as we understand the whole process, that may become something to preserve keep the interglacial going longer than normal. So these are the kinds of consequences we're looking at. No one knows any of them for sure. But in the context of our finely tuned, balanced food versus consumption world, these things could be very, very bad. Let's go ahead. Let's talk just a little bit about what the models say. This is international. This is a Canadian model, a United States model, and a UK model. And these are temperatures in which they predict 4 degrees warming. So if you want to, the going feeling right now is it's going to be more like 2 degrees warming. So you have to divide all these things by 2. But yellow here is about 2 to 4 degrees, and orange here we're up to 6 to 8 degrees. And so you can see there's a real problem in that the average warming might only be 2 degrees centigrade Celsius, but in the northern land masses, you can see considerable more warming is predicted. And they don't agree in great detail, but they agree in generality. Let's go to the next view graph. Here's soil moisture, and yellow is bad, green is good. And you can see, boy, it got warm and there was CO2 and there was rainfall, so we're going to be in good shape. No, because the net effect is that the soil moisture is going to be low. And so these models, if they're correct, and they may not be correct, but they're probably good enough to signal a concern that the places where you want to grow things aren't going to be as moist as you like. The big commodity in the 21st century may not be gold, it may be water, fresh water. Let's go ahead. Well, now we're to the challenge, and according to my schedule, we were supposed to be to the challenge 5 minutes ago, so well, I'll talk very quickly. One of the challenges I think we have to do is to stop thinking about the Earth the way we used to think about it 2,000, 3,000 years ago. Keep in mind there's 5 great apes in the world. In evolution, being a great ape is a lousy evolutionary solution. 4 of the great apes are in danger of extinction because they're very specialized and they can't adapt and they're on their way out. We happen to have a big brain, and so we're making it by being able to adapt to almost anything. But we didn't do that right away, and for most of our cultural history, humans have had to fight with nature as an enemy to conquer it, and they've had to increase their populations as fast as they can as a hedge against diseases and infant mortality and such things. We have to stop thinking of the Earth as something that has to be conquered and subdued, and think of it more as this beleaguered friend, which is the only place we know how to live right now, and we have to begin to think in terms of stewardship. We've got it conquered, and we're wearing it out like an old rug with too many people walking across it. And so other people have always come and called that into question, and I thought I'd be a little romantic and say that there were people here on the North American continent who 100 years ago really couldn't figure out what we were all about, and they're probably even more mystified now. Let's go to the next view graph. This is a world premiere. If you can move it up just a little bit so you can see the bottom. This is the frontispiece that you'll be seeing in publications, this and that, for the Laboratory Environmental Studies Ethics Group, Our Common Ground, founded by Francis Menlove. And I think many of you recognize Oppie. And there he is thinking, and it's sort of a gray, has the Los Alamos Laboratory contributed to the destruction of the Earth? And about that time, after the first 50 years, things have changed. And the name of the town is Los Alamos, of course, which means the shade trees, mainly cottonwoods. And here comes Populus fremontii. I slip into Latin when I talk about plants a lot. A nice green leaf of hope added to a very thoughtful person who has always called upon us in his writings and thinkings to use our best ideas. And so we'll see a lot more of common ground. So there's a challenge to think about things a little bit differently. Let's go on. Real quickly, what's Los Alamos already doing in terms of the challenge? Well, we're trying to work with everybody we can in this area. The DOE has decided to really get into worrying about global change in a big way, and ARM is atmospheric radiation monitoring, look at sunlight and cloud interactions, and go out around the world and set up observational sites to help develop the computer codes. CHAMP is computer hardware, which would make the codes faster, advanced mathematics, which would make the codes faster, and model physics, which would improve the codes. And we have the lead, Bob Malone, down at the ACL. C3 is leading the DOE's whole effort in the massively parallel part of CHAMP to work on this. And Los Alamos has done quite well in the competition for funds to do these things. It says 4 and 3 projects, but there were only about 10 or so in each one of these that were given out. And so we're working very hard with the Department of Energy in response to what it's doing. High-performance computing initiative you're hearing a lot about. Los Alamos is being very successful in that area, working on that. There's a whole lot of work to have very rapid transmission lines. We're working with people at UCLA in which we are looking at the possibility of running an ocean model here on a massively parallel processor while they're running the atmospheric model on a different machine and having them communicate with each other. And then the DoD keeps wanting to get into the effort, and we have been working with them on that. Let's go ahead to the next view graph. At home here, the laboratory has been, I think, quite forward-looking. John Wetton has been very supportive, continues to be. And we have internal funds to work on climate research projects, to build up our effort. IGBP has been very pleased to be a gathering place for people from all many divisions to come and learn and argue and go back out to do work. And you can see a bunch of the things we're doing, and that S was to remind me that when I made this view graph, Don Cobb and SST division hadn't really hit their stride on the possibility of making small satellites that can make observations. But we're now starting a collaboration with Sally Ride and the people at CalSpace to look at the possibility of launching very small satellites which could bridge the gap, if you will, till NASA gets their big ones up. And Los Alamos is very good at that kind of thing. And so, you know, if I began to write the other things we could do, I'd have lots of green ink all over there. We're also working with the University of California, and the fact that the university manages us and we work with them is a very strong point. And I would like to see many more of these collaborations, not just in climate change, but other things. But that's being a very big help. We're working with 4 different campuses and with Scripps, as you can see there. Let's go ahead. Our observational capabilities are as high-tech as everything else at Los Alamos. This is a little telescope with some mirrors, and it's got a LiDAR. You can drive around in this truck and fire that LiDAR out over an area like this. This is down at White Rock Overlook, you'll probably recognize. But the people who have been trying to study the soil moisture and the plant evapotranspiration have been wringing their hands at how to do this right. And this little guy can do a whole area of a few kilometers on the side, up and down, and time dependent, size dependent, and has done an awful lot already to help us understand that very well. We're working with UC Davis doing this, and we've been out to Penn State and some of the universities in Arizona to work on these things. So this is the picture that says we're doing a lot of observational work, and there's much more of it than just this, but this is one to show it. Let's go ahead. Well, here's the Los Alamos global climate model. What on earth is a global climate model? Well, first of all, you break the Earth up into 5-degree squares, and you end up with lots of 5-degree squares. And then you break it into 20 layers high, and then 6 layers down in the soil. And you put in the chemistry and the surface physics for how the moisture comes out of the soil and how the sunlight goes into it and goes into the soil when it rains. You put in clouds, go up to 70 kilometers high. You put in the sun's angle-dependent diurnal flux and lots of other things to make the model work. And you run the model and see if you get any results that look anything like the Earth. Let's go ahead to the next view graph. Here's just one day in July from that model. The big reason I show you is this is how big these cells are. You can see there's one right there. And so all around the Earth, that's pretty good zoning to see the whole Earth. But if you're trying to look at California, one of those zones goes from San Francisco Bay to Death Valley. And you can see that it's a little hard to look at the very important subgrid scale things. You don't get the Himalayas quite right, so the monsoon moves around. And so we do need finer zoning, and that will, of course, need much bigger computers, much faster, which we're heading toward. Let's go ahead. This is the kind of thing you get when you run the codes. No matter how I play with the parameters, the model keeps coming back, the same thing. 40 days and 40 nights. Let's go ahead. Next view graph, yeah. I thought I'd stop for a minute. Every now and then when you have diagrams and lines and cartoons and pictures and models, it's nice to stop and look at what it is we're really worried about. I don't think many of you can look at this little bird flying over this incredible scene without having a real intellectual and emotional response. But that's what we're talking about. We're talking about the moisture, which is what the sunlight is scattering off here, the clouds, the oceans, and the things that live here. This is what's at stake, and this is what we're working hard on. Let's go ahead. Next view graph. Very quickly, working with the Scripps people, they have the observations. We have this is Los Alamos, December, January, February, so this is winter, and this is rain precipitation. You can see that we're not doing too bad. We predict a lot of rain, over the Amazon, and sure enough, there it is. We predict this whole tropical convergence zone, and we're getting that. And we predict that there's no monsoon in the wintertime in India, which is sort of nice. Let's go to the next view graph quickly. Sure enough, there's the monsoon. It's not raining in South America. And so while in many details we're not happy with it, there's a lot we like. We're able to do the generalities of what the Earth is doing. Let's go ahead. I'm going to skip this because we're out of time, but it is some comparison of satellites with models. Can we go to the next view graph? This is got a map of the world. There are 5 stations around the world that are picking up methane gases and CFCs, chlorofluorocarbons, and we know what the sources of those are in the northern hemisphere. There aren't any in the southern hemisphere. And so we can run the model and have it transport these gases around and try to see if we get the observations in the southern hemisphere. There's a real problem with getting gases to go from the northern hemisphere to the southern hemisphere because of that huge rising Hadley cell turns everything backwards. And in some of the other computer models around the world, which aren't so vertically accurate as ours, they are not getting it. We're getting some pretty good results. And one of the things we're asking ourselves is, how is the stuff getting to the southern hemisphere? And we began to think that maybe our vertical zoning was good enough that it was allowing stuff to pop over the top. And what we did was we decided to try to run a movie to see if that would do it. And I want to show you that movie. But let's look at the next view graph because I'll set up what you're going to see. Turn that thing, rotate that clockwise. There, all the way around. Now what we've done is spread the Earth out. This is the North Pole, that's the South Pole. The equator runs right along in here. And this is the concentration of this chlorofluorocarbon. See, it's mostly in the northern hemisphere and it's trapped there. This is something which, if you put it down to a point on the globe, wouldn't be anything. So you don't have to think much about that. But look at this hot spot. This is a little puff of gas from this high concentration up over North America, floating over the top and going down to the southern hemisphere. And what you're going to see is a movie of a sideways picture of this, so you'll see that on the average nothing's getting down. And then there's a movie of just at the equator, as if it was a fence, altitude versus equator. And let's see that movie right now. Here you can see, if this is the equator, and this is up in Canada, and this is down in the south, the high concentration can't get across because the Hadley cell turns it back. This is averaged all the way around. But if you look as if you had a big fence at the equator, you can see that periodically, up high, higher than Mount Everest, these plumes of high concentration chlorofluorocarbons are going over the top. And you get a hint at them doing that here. This is averaged all the way around so you don't see the yellow. And it's very time dependent and very three-dimensional. And if you don't have very fine zoning in this region, you won't see it at all. And so we're guardedly optimistic that the code is doing it right and is showing us something we didn't know in the first place. And of course, this can cause us to recommend certain kinds of airborne observations to verify this. So that's 9 months in sending chlorofluorocarbons south. I'm going to rush on to the end here. What should we be doing? I had a slight policy statement I was going to read. I don't have enough time. You probably don't want to hear it anyway. But what it essentially says is what we really should be doing is not having a great crash program. Some university guy said we needed a Manhattan Project, and I was going to suggest if you have one, have it where we had the first one. But what we need is like a standing army in global change. We need to be much more serious about studying global change, the oceans, the atmospheres, the things we're doing, because there are many different things that a society as large as ours can do to the atmosphere and the oceans. We need to understand them. We need a long-term, large effort, and we need it to be centered in the universities and at some of the other institutions, but certainly the weapons labs, which are turning their efforts to other things, are candidates for a tremendous contribution to that. The DOE currently is not doing any study in global change. It's studying how to improve codes so that somebody else, somewhere else, will do it. And we're trying to convince them that that's a noble thing and a good start, but they really ought to have a stronger program of their own. Let's go to the next view graph. Here are some of the things that Los Alamos could be doing in terms of helping out global change. You don't have to just study climate. There's a whole area of energy conservation we've worked in the past and could work in again. The concept that nuclear reactors might make a comeback is one that would be amazing to me, but I'm not saying it can't happen, especially with the kinds of new designs and with the accelerator transmuted waste program which we're looking at, which would alleviate our waste problem. Photovoltaic cells may really be very important in terms of energy production. And finally, we're very good at waste storage and transportation there. So those are some things that the laboratory could do in addition to the global change studies it's doing. Let's go on. This is from the IPCC report. A major dilemma in the issue of climate change due to increasing emission of greenhouse gases in the atmosphere is that the actions required well before many of the specific issues that are and will be raised can be analyzed in time to do it. That's the problem. We've got to know what to do before we know what the problem is. And so this is one of the things that gets in the way of trying to figure out what action to take. Let's go on. Here's a lady doing some mitigation. This is Mrs. Alice Snoot of East Icicle, Vermont. And she's trying to put as many CFCs in the atmosphere as possible to warm it up around her place, especially around February. What Mrs. Alice Snoot doesn't know is in the United States, at least, in 1978, CFCs were banned from these spray cans she's two-fistedly using here. And Europe has banned them now, too. Yeah, there are a lot of different ways you can think of mitigating. You can even make it worse so it'll be warmer. Let's go to the next view graph. Mitigation, anyone? The alarmists, I think, are good and bad. They cause us to be concerned and get a more considered opinion. The costs between Amory Lovins and the National Coal Association are anywhere from we can make money on this to we'll lose an awful lot. People are working at that, and we had a big conference 3 weeks ago to discuss just that issue. Conservation seems to be the important thing, then transition, for instance, natural gas away from coal, and then to no fossil at all. I probably didn't spell that right, did I? Do we have time? Some people, Schlesinger, who's a great climate modeler at University of Illinois, is saying we probably have about 10 years, but our bureaucracy takes that long to get going doing anything. So I think that's the same as saying we don't have time. Couldn't we just adapt? The National Academy of Sciences said that, yeah, we could in the United States. To be a little hard on the farmers, and of course the trees and the animals wouldn't be able to adapt, but what's a few trees and animals to the National Academy of Science? And so this adaptation is something that people are looking at. It's an awful lot like somebody with terminal cancer who has gone into the denial phase. The United States, to some extent, is psychologically in a denial phase. But that's not a bad way to go, because some things which are incurable turn out to be curable. Why won't we plant trees? Yes, 10 to the 11th trees will do the trick. Since only 1 out of 4 trees grows to maturity that you plant, every man, woman, and child in the world will have to plant 100 trees next year. So the thing is to make your best guess and try a no regrets policy. You've probably heard that, which says let's take pollutants out of the atmosphere that we want out anyway. Let's head in a direction that is better for the Earth. And then if the warming turns out to not be as bad as we thought, we're still in good shape. And if it is as bad, well, we started early. Let's go to the next view graph. We're almost done. A way to think about the future. We have not so much inherited the earth from our parents, we are borrowing it from our children. Those 2 acres that you have to live on, your grandchildren want to live on them too, so take care of them. There's a way to think about the future, about the present too, and I wrote this down. I think this is a real true statement. A prudent person doesn't like what he or she sees. A curious person wants to know what the heck's going on, and for 50 years Los Alamos has been attracting those kind of people. And in conclusion, I'd like to think that when those children inherit the earth from us, they will be impressed by our efforts at Los Alamos to understand and to preserve. Thank you.
We'll take a few questions.
Some years ago, University of Illinois conducted a cloud survey, found that they believe contrails from airplanes modified the insulation by 20%. This this was many years ago before there were as many jet planes as now. I don't know if their number was anywhere close, but it sounded like there's a very important effect.
You can watch it here around Los Alamos on certain days when the contrails spread out and give you a gauze over the whole thing. And locally that's true. As a global phenomenon, it's not clear how true it is, although I'm told there are right now, as we speak, 10,000 aircraft in the air over the Atlantic Ocean alone. And certainly the move to supersonic jets, which would go into the stratosphere, which is much more dangerous because stuff up there stays there. It doesn't get rained out like it does in the troposphere. These are things we have to pay attention to. The atmosphere has a way of adjusting for those kinds of things if they're just minor. But you have to worry about it, yeah.
Jack, it seems like you soft-pedaled the ozone depletion. And the CCF, the CFCs rather, and the role it plays in cleaving the ozone.
I hope I didn't give that impression. I think it's extremely important. It's just one of the things that we can fix. The other ones are very difficult to fix. The whole story of how they found the ozone hole, the chemistry in the ozone hole in Antarctica is very different from the one that's depleting the ozone over our heads, and that's why it's not so bad over our heads. So it was very nice we got a little early warning on that. People were caught flat-footed because no one thought about what's called heterogeneous chemistry, namely some of the chemical reactions, not involving ozone but involving chlorine, would take place on the surface of ice crystals in the very cold polar night. The Antarctica gets so cold that it forms a large number of what are called stratospheric clouds as the water vapor freezes, and that provides surface area for certain kinds of exotic chemistry. The thing that's neat is while the atmospheric chemists were fooled by that, if you follow the story, the detective story, they very quickly figured out of the 5 or 6 different models for why we were losing ozone down there. They very quickly figured out which one it was, and then they began to make predictions for the airplanes to go in and make observations. If this model is right, the chlorine oxide, ClO, will be greatly enhanced. If it's right, the nitrous oxide, which gets rid of the chlorous oxide, will go away because it's, the vortex allows it to be depleted. And they began to make specific predictions, and each one of those predictions were found to be correct by the aircraft. And so they went from being fooled, blindsided, if you will, to a predictive mode. And I think no knowledgeable scientist now thinks anything but that the ozone hole is human-generated over Antarctica. And that now has gotten the interest up for the other kind of chemistry, which is reducing the ozone over our heads as we speak by as much as 5% in the 5-6% in the winter and 2 and 3% in the summer. And that's going to get worse because the chlorofluorocarbons have a long lifetime in the stratosphere. They don't go away. Even though we stop putting them in, we still have to wait for the ones to get out. So I didn't mean to say that. I think it's a terribly important thing. The only nice thing about it is we can do something about that one easily.
Last question.
Yes. An important aspect of that is whether volcanic emissions of HCl are more important than CFCs going into the atmosphere. Could you address that?
There's no doubt about the fact that several different kinds of greenhouse gases are put into the atmosphere by volcanoes in enormous amounts. Volcanoes do both, though. They put up the sulfates, which turn into aerosols, which scatter the sunlight back out and cool the Earth down. We've had dramatic coolings, whole times when there was no summer at all due to volcanic eruptions. And we expect this one by Mount Pinatubo to really have an effect on our climate. So volcanoes go both ways in this, and indeed they do that, and that causes variations in the ozone. And after all, Antarctica has Mount Erebus, its very own volcano, but those things are taken into account. We know about what those things are doing, and the ozone hole in mechanism for reducing ozone in the wintertime in Antarctica has always been true. It always has reduced a little bit. I probably could I'd love to give a whole talk on just the ozone hole. And volcanoes are a big perturbation. They may be why that temperature record is so ragged. And so, yes, that's an important thing to worry about. And one of the fun things at the lab is we have a big program to study volcanic eruptions, too.
In closing this colloquium, I'd like to thank Chick, and I'd also like to thank those who have participated in and developed our global change program. Sumner Barr has worked tirelessly with Chick, with me, with others to get the program going, and we expect it to be a vigorous and continuing activity. Also like to thank my colleague Terry Dreiser for providing some of the funding, at least initially, to get the program started. Chick, thank you very much for the extremely